Bismillahirrahmanirrahim. Assalamu alaikum dear students. I welcome you to the next session of the C Refresher video lecture series. The idea of today's session came to me when one of my students emailed me a piece of code which when executed does not make any sense to him. Let us take a view of that program. So this is the program which he emailed me. Which once executed, of course, asks me for a number, and if I give the number as 32767, as per the logic, it adds 10 to that number and displays that number. That number has to be 32777, but it appears minus 32759. Another important thing to note is that if you run this program many a times, it gives the same output. To understand the problem and solve it, we need to have a very clear understanding as to how information is stored in our computer memory. Let's first restrict ourselves to this information as signed or unsigned integers. Let me move on to the board, and I assume that you have a very fair idea as to how numbers are represented. Let's suppose different data types. I assume that you all know how to convert between the decimal, binary, octal, and the hex representation. For example, you all must be knowing that this is a base 10 number, and this is again a base 10 number. In binary, we can say that this is a base 2 number in 8 bits, and this is a base 2 number in 8 bits, that is 255. And similarly, if I talk about hex, then this is 0 in base 16, and FF is basically 255 in base 16. Like all the other languages, C also supports multiple data formats for both integers and floating point data. For example, we have integers, and in integers the data types that are supported are short, which can be signed as well as unsigned, int, which can be again signed and unsigned, long, and long. If we talk about the character data type, we have the char, and it also can be signed as well as unsigned. If I talk about floating point numbers, we have float, double, and long double. Now the question is, what is the maximum or minimum value that can be contained in these data types? Let me change color. Max and min values. That is the range of these data types. Well, the answer to this question may vary depending on the type of the platform, that is the hardware and the OS, which can be 32 or 64 bit. as well as it depends on the compiler. Well, as far as the size is concerned, we can use the size of operator to find out the size of these data types. Let me move on to the terminal and show you a program which uses this size of operator to compute the size of the character, short, int, long, 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 float, double, and double, double. Let me compile this. And it tells us the size of character is 1, short is 2, integer 4, and long double is 16. Let me write this over here. So we have, on my machine, short takes 2 bytes, integer takes 4 bytes, long take 8 bytes, and on my system right now the long also take 8 bytes. The character take 1 byte, float take 4, double 8, and long double 16. Let me confirm long, yes, long is 8. Probably the larger data size support is not enabled by default. Okay, so let me check out again on this the hardware. My hardware is 64 x86 64-bit, and the release of the kernel is 4.6.0 Kali AMD 64 again. As far as the compiler is concerned, it looks for the header file limits.h. Let me get that for you. usr include limits.h, and over here you can go through with this file and find out the min max values of different data types: character min, character max, and so on to short min, short max, unsigned short 65535, int min, int max, and so on. Other than looking at the file limits.h, you can use the command getconf. The getconf command, let me less it, gives you the limits of lot of parameters that we will be using later on. But right now you can see the long pet is 64. You can see the int min value is this and int max value is this. You can use getconf and pass it arguments like char min. This is the minimum value of assigned character. Max, getconf char max 127. And similarly, if you want to go for the unsigned, you can use this. Let me put a capital U over here, 255. So since char is character data type is of 8 bits, so the maximum unsigned value is 255. Now before proceeding, let us try to understand how multiple bytes get stored in our memory. Let me move on to the board. And let me take white color again. I'm going to discuss multi-byte load and store. Well, let's suppose that we have a 2-byte variable that is short I is equal to 54, and in 2 bytes we can write 54 as let's suppose 1, 2, 4, 8, 16, 32, 64. I think I will manage within this. Let's make 32 1 and 16 1, and let's make 4 and 2 1, rest all zeros. So 8 bits 9, 10, 11, 12, 13, 14, 15, 16. So these are the 16 bits in which 54 is represented. This is the lower byte and this is the upper byte. So let's suppose that here is the memory. Let's suppose this is address 99, this is 100, this is 101, this is 102, and this is 103. And let's suppose I want to store this variable I at address 100. Now the question is that I need 2 bytes for this. This is the lower byte, let me call this byte 1, and this is the upper byte, let me call it byte 2. Now will this byte 1 will go to the address 100 and this goes to 101, or this will go to 101 and this goes to 100. So if we use this option, that is store the least significant byte, that is byte 1, at the smallest address, that is 100. So writing 0 double 0 double 1 and 0 1 1 0 over here and 8 zeros over here. If we write the least significant byte at the smallest address, then this is known as the little endian scheme. And if we write the least significant byte at the largest address, that is this way, then this is known as the big endian technique. Intel machines supports little endian, and if you happen to have a MIPS machine, that is going to support big endian. So remember, for all practical purposes, if you are storing multiple bytes inside the memory at a particular address, for example 100, the lowest byte will go to the lowest address, and that is the little endian technique. Now the next question that arises over here is, how much maximum data we can store in a byte? So let me start from 1 bit. If I have 1 bit, I can store either 0 in it or a 1 in it. That is, I can store 2 values. If I have 2 bits, then I can store either 0 0 or 0 1 or 1 0 or 1 1. That is 2 raised to power 2, 4 values in it. If I have 3 bits, then I can store 8 values in it, and so on. If I have 8 bits, then I can store 2 raised to power 8 values in it. That is 256. Let me move on to the next board. And let me say that if the storage is unsigned, for unsigned storage, suppose that I have a storage of n bits. The maximum value that I can store is 2 raised to the power n, and starting from 0, it ranges from 2 raised to power n minus 1. So for 8 bits, it is 0 to 2 raised to power 8 minus 1, that is 255. And similarly, we can compute the rest as well. Well, then, as far as the signed numbers are concerned, it depends on the representation style of a signed number. A very common style is known as signed magnitude. Signed magnitude. Let me take rubber. SI Gn, sign magnitude. In sign magnitude of representation, we keep one bit for the sign and the rest of the bits are kept for the number. So the range that can occupy using a sign magnitude is from -2 raised to power n minus 1 to plus 2 raised to power n minus 1 . Well, we normally do not use this in our computer system because of two reasons. The first, that it has two ways to represent 0. We can have a positive 0. If I talk about 4 bits, we can have a negative 0 if we talk about 4 bits. The other important point is that normal binary arithmetic rules do not apply to this sign magnitude representation. Let me try to add a +1 and a -1 using a binary full adder. Let me change color. Let me write a +1 in 4 bits. This is a +1. Let me write a -1 in 4 bits. This is a -1. Now let me add it. We add 1 and 1, we get 1 carry, we get a 0 over here, we get a 1 over here, we get a 0 over here, and we get a 1 over here. So if we add +1 and -1, we must get 0, but the answer over here is -2, which is wrong. So instead of using sign magnitude, our system use another technique, and that is known as 2's complement. And 2's complement do not suffer with these limitations. That is, it represents 0 in one unique way, and it easily manipulates the number. You can perform all the operations on it. And let me repeat the same example of the addition as I have shown over here, that it doesn't work with the sign magnitude, but it will of course work with the 2's complement. Let me move on to the next board and show you. Let me write down the +1, that is, and let me write down the -1. I think you know how to write +1 and -1. You take 1's complement and you add 1 in it. So anyway, so this is a +1 representation of using 2's complement. This is -1 representation, and we should get a 0 over here. So let me do the binary arithmetic. 1 + 1 is 2, that is 1, 0. 1 and 1 is 2, that is 1, 0. 1 and 1 is 2, that is 1, 0. 1 and 1 is 2, that is 1, 0. So this is what is 0. So normal binary arithmetic rules apply if we follow the 2's complement way of doing things. And as far as the range is concerned, the range is -2 raised to power n minus 1 to plus 2 raised to power n minus 1 minus 1. So we have one additional negative number because there is only one way of representing 0. So if we have 8 bits, and if we are talking about the signed numbers, it can range from -128 to +127. If we have 16 bits, it can range from -2 raised to power 15 to, of course, +2 raised to power 15 minus 1, and so on. Now, after having an idea of this, let me move on to the console, and let's find out the ranges of different programs using the same concept. To save time, I have written a program for you. Let me get that for you. Size, range. Okay. Okay. So this line, if I use this line, this says size of short is 2 bytes, 2 into 8 is 16. So I get 16 in this variable. I just want to find out what is the min-max range of short for signed as well as unsigned. And if I talk about unsigned, it will start, of course, from 0 and it will range to this value. I'm using a bitwise operator, the left shift operator. I'm doing a left shift with 16. So once 16 times 0 is pumped in, we get 2 raised to the power 16 minus 1. So this is 2 raised to the power 16 minus 1, from 0 to 2 raised to the power 16 minus 1. And if we talk about the range of signed short, this is not integer, this is short, as in bits we have 16. So we are left shifting this 1 by 16. So left shift by n bits means multiplying by 2 raised to the power n. So this becomes 2 raised to the power 15. From minus 2 raised to the power 15 to plus 2 raised to the power 15 minus 1. Let me compile this program. So you can see we have 16 bits for short, and the range for unsigned short is 0 to 65535, and range of short signed short is this. Let's check out the same with getconf command. shrt min and shrt max and unsigned shrt max. So these are the same values. So using the same left shift technique, you can compute the range for all the integral data types in the same fashion. Now, gentlemen, let's review the buggy program again. And now I think it's very apparent that the problem is with this line. Once A is having a value which is already the upper limit of short, let me compile this, buggy 32767. So this is already the upper limit of short. So once we add 10 to it, an overflow occurs. And gentlemen, as you know, that overflow is a condition that occurs when a calculation produces a result that is greater in magnitude than what a given register or storage location can store or represent. So if I run it again and give it a smaller value, let's suppose 200, so it will give the correct result. So let me move on to the board again and try to explain it to you by doing a bit of arithmetic. Okay, so actually we are going to do is we are going to add 32767 with 10, and both these numbers are represented in 16 bits. So 32767 in 16-bit can be written in hex as 7FFF, and 10 can be written as 00AA. So let me add this up. If I add F with A, I get 19 in hex. 1 goes in carry. F and 1 becomes 10. 1 goes in carry. 1 and F goes 10. 1 and 7 is 8. So this is a hex number. If I write in binary, it is 1000 0000 0000, and 9 can be written as 1001. Now since 8 and 8 and over here we have 1, so the computer takes this as negative number, which is in 2's complement. So the computer takes 2's complement of this, and taking 2's complement of this is, this 1 remains as it is. We get 110, we get 1111, 1111, and 1110. So this is a negative 7FF7 base 16. And if I convert this to decimal, this is minus 32759 base 10. And this is what actually the answer that we get once we run this, minus 32759. So this is the same number that we are getting over here. Hope with this brief arithmetic you have come to know the issue, that the issue is things are being overflown. Now that we know the problem, let us try to correct the buggy.c. Actually what I need to do is I need to increase the container. Let A be as it is, and let me increase the container B. So now B is an integer, so this should work now. I give the same output, that is 32767, and after adding 10 in it we get 32777, which is the correct answer. Right, students, for integer numbers, let me take the board again and let me change color as well. For integer numbers, we can detect an overflow after an addition operation. How we can detect an overflow? Check the sign of the both operands as well as the result. If the operands have different signs, that is, one operand is positive and the other is negative, overflow will never happen. And if the operands have same sign, let's suppose both operands are positive, but the result is negative, that means an overflow has occurred. Similarly, if both operands are negative and the result is positive, we again say that an overflow has occurred. So this is how numbers, integral numbers, are stored in our system and how they are manipulated. And let me take this opportunity to briefly touch upon the real numbers as well. Let me change board. So as far as the real numbers are concerned, we have two ways of representing them. One is the fixed point and the other is the floating point. Of course, our computer systems use floating point, but let me start with the fixed point. The fixed point representation. let me take a number. Let's suppose 12.6. This is a decimal number of base 10, and of course we can convert this to a binary number. Let me do the math for you for your revision. 2 6 the 12, remainder 0. 2 3 the 6, remainder 0. 2 1 the 2, remainder 1. So 12 can be represented as 1 1 0 0. Now as far as the fractional part is concerned, we multiply it with 2 and we get 1.2. We multiply the fractional part again, we get 0.4. 0.4 is multiplied with 2 again, we get 0.8, and if we multiply 0.8 with this, we get 1.6, and this process goes on, and we take these numbers in this fashion, and this is 1 0 0 1, and if you continue this, you will see that it follows this pattern: 1 0 0 1 1 0 0 1 1 0 0 1, and so on. Now to represent this number as a fixed point, we basically take three parts of it. The first part is the sign, which can be positive or negative. The second part is the integer field, integer part, that is 12, and third is the fractional part, fractional field, which is 0.6 over here. Now we need to decide how many bits we are going to use to save this. Let's suppose we take 32 bits, and if we take 32 bits, let me take 1 bit for the sign. 0 means positive, 1 means negative. Let me take 15 bits for the integer part, and let me take, suppose, 16 bits for the fractional part. So this sum up to 32 bits. So this is a 32-bit representation. Let me change color and write the number over here. I write a 0 over here because the sign is positive, and then as far as the integer field is concerned, that is 12, and that is 1 1 0 0 0 0 0 0, and so on to, so these are 15 bits. And then we have the fractional part, 16 bits, and that is 1 0 0 1 1 0 0 1 1 0 0 1, and so on. We just write 16 bits over here. So using this fixed point representation in 32 bits, what is the largest number that can be stored using this way? The largest number that you can store is, let me change color again, 0, then we have 15 ones, and then we have 16 ones over here. So this makes 2 raised to the power 15 minus 1, and this part makes the fractional part 1 minus 2 raised to the power minus 16. So this is the integer part, and this is the fractional part, and this comes out to be almost 32768, closer to 32768, or you can say 32767.99999. And as far as the smallest number is concerned, using the fixed point representation, and let me use this. So in the integer part we use all zeros, 15 zeros, let's suppose, and over here we use a lot of zeros, and in the end we have 1. So this is the fractional part, this is the integer part, and this is the sign. So this is about 2 raised to power minus 16, which comes out to be around 0.000015. So one of the biggest advantage of using this fixed point representation is performance. As the value stored in memory is an integer, the CPU can take advantage of many optimization techniques that modern computers take, and it does not require any additional hardware. For example, a floating point unit for multiplication and addition. The downside is apparent. This representation has a very limited range of values, a very small value. So let's move on to another representation that is called the floating point representation, and that floating point representation was introduced in 1985. Floating point, and it has been accepted as a standard by IEEE. So let me write down IEEE standard for floating point. It was introduced in 1985 and is based on scientific notation. And by scientific notation, as you might have read in the school days, plus minus mantissa into 10 raised to the power, what is the value of the exponent. The current version of this is IEEE 754, revised in 2008. As far as the storage layout is concerned, we have single precision, which is of 32 bits. We have double precision, which is of 64 bits. We have do have quadruple precision, QUAD RGPLE precision, which is of 128 bits. And finally, some systems do support octuple precision, which is of 256 bits. Well, in a similar fashion, we have three things which we need to store, and that is the sign bit, the exponent part, and the mantissa part. This is the mantissa part, this is the exponent part, and this is the sign part. So if we talk about single precision, 1 bit is reserved for the sign, 8 for the exponent, normally in excess 127 notation, and 23 for mantissa. If I talk about 64, 1 bit for sign is enough, 11 bit for exponent, and 52 bits for the mantissa. Quadruple, 1 bit for sign, 15 bits for the exponent, and 112 bits for the mantissa. And finally, for 256 bits, we have 1 bit for the sign, 19 bits for the exponent, and 236 bits for the mantissa. Remember, gentlemen, as far as the exponent is concerned, the base is implicit, that is, the base is 2, and this exponent field represents both positive as well as the negative exponent. So this exponent represents both positive as well as negative exponents. To do this, a bias is added to the actual exponent in order to get the stored exponent. For single precision, the value of the bias is 127, and for double precision, the bias is 1023. So for example, to store an exponent of +3, you actually store 127 plus 3 is equal to 130. And similarly, to store an exponent of let's suppose -3, you actually store 127 minus 3 is equal to 124. So the more the number of bits over here in the exponent part, the larger is the range we can cover. And as far as the mantissa is concerned, the more the number of bits to store mantissa, the more precise the representation becomes. This mantissa is also called the significant, that represent the precision bits. So let's see how we can store values using floating point. We have seen how we can store 12.6 in fixed point. So let me move over here and see how we can store this. We know that 12.6 can be written as 1100.1001 1001 1001 and so on. So we need to normalize it. By normalizing, I mean I need to bring this decimal point to a place over here such that on its left we have a 1, which we are not going to store, and it is implicit. 1.100, and then this part comes over here, 1001 1001 1001 and so on, and we multiply this with, since we have moved the decimal part to 3 positions left, so we multiply it with 2 raised to the power plus 3. So now this is what we need to store. This is a sign, and this one need not to be saved. This is a sign, and this is the mantissa part. This base is need not to be saved. And this is the exponent, and this exponent is saved in excess notation. For 32-bit it is excess 127 notation, and for double precision it is excess 1023 notation. So if we want to store it in 32 bits, let me change color now. 32 bits, it will be something like this. 1 bit for the sign, and then we have 8 bits for this, and 23 bits for this. So sign is positive. We have positive sign, so we put a 0 over here. And as far as the exponent is concerned, so over here we save the exponent as +3 plus 127, that is 130. 130 can be written as 1000 and 0010, and here comes the mantissa, that is this part, which is of course 1001 0011 0011 and 0011 and so on to 23 bits, whatever. And if I write in hex, it becomes 0x414999 and maybe 3 more lines, 1 2 3 4 5 6 7 8. So we have this much. So this is how it is stored. Now after having seen how the numbers are stored using the 30-bit floating point IEEE 754 standard, let us see the max min values. Max min. Let's see the ranges. Let me move on to a new board, make it black. Okay, now let's see the range of single precision. Range of single precision numbers. As we know that the single precision numbers come in 32 bits. Let's first calculate the smallest value. So you have 1 bit for the sign, 8 bits for the exponent stored in excess 127 notation, 23 bits for the fractional part. So the sign can be positive or negative, and the exponent is 00000001, and the fractional part is all zeros. So the actual exponent is 1 minus 127, that is minus 126. So the range is plus minus 1 point, fractional part is 0 multiplied by 2 raised power minus 126, which can be written as plus minus 2 raised power minus 126. So this is quite a small value that we can manage in single precision. Let me change color and talk about the largest value. For single precision, again we have 32 bits, 1 sign bit, 8 exponent, and 23 for the Mantis part. Sign can be positive or negative. The exponent can be 1111, 1110. Remember, exponent of all 8 zeros or all 8 ones are reserved. In the fractional part we have all ones. So over here the actual exponent is 254 minus 127, that is plus 127, and the number is 1.1111 into 2 raised power plus 127, which is plus minus 2, almost 2 into 2 raised power plus 127. So this is quite large values. Now let me talk about the precision as well. Let me move on to the other board and take white color. If we talk about precision, if I talk about precision for floats, and we know floats are stored in 32 bits, and in those 32 bits the fractional part has 23 bits. So 23 multiplied by log of 2 base 10, which is 23 multiplied by 0.3, which is nearly equal to 6. So 6 decimal digits of precision are available to us if we are using 32 bits, single precision. And if I talk about the double data type NC, which is in 64 bits, we have 52 bits for the fractional part. So 52 multiplied by log of 2 base 10, which is 52 multiplied by 0.3, almost equal to 16 bits. So for double we have 16 bits for the precision. Let me touch upon the underflow as well, the concept of underflow. We have seen overflow. In floating point as well, overflow can occur. For example, the largest magnitude value might be rounded to infinity. The largest magnitude value is 1.1111 multiplied by 2 raised to power 128. The largest magnitude value is this. This is the largest magnitude value. If the value is more than this may be treated as infinity and your programs may not behave properly. So you must be watchful for overflow in the floating point arithmetic as well. As far as the underflow is concerned, this term typically applies to floating point numbers for example, a value smaller than the smallest magnitude value, that is less than a value less than 1.0 into 2 raised to power minus 149. Such numbers are often rounded to 0. They are made 0, which may not be what you want to happen. It may have a very small effect on addition operation, but a very large effect on multiplication operation. You might be wondering why the smallest magnitude in single precision is this, and why not plus minus 2 raised to power minus 127. Students, this is because there is a bunch of numbers called denormalized numbers. Denormalized numbers, which allow floating point numbers to get very small by sacrificing the number of the significant bits. Anyways, dear students, I think that's enough. So you must remember that while writing portable programs, keep all these points in mind which we have discussed today. Your programs must detect any overflow or underflow and raise an alert whenever that occurs, and you should handle those accordingly. It is very important to write what we call portable programs. Hope today's session was informative. I wish you all the best. Happy learning and Allah Hafiz. जहां का सबात है तुम ही से ऐ मुजाहिदो जहां